right? So moment about Z at point A is equal to Py multiplied by L. Okay. If I pick a point, if I were to pick another point, and this point is my point C, and point C, if we look at the distance from here to here, right? This is our L2. Then MZ at point C, right? At point C is equal to Py multiplied by L/2. Okay. So we now note that P moment at Z at point A, right, is greater than moment at Z at point C. Okay. So that's why I say failure will occur at point C. Okay. So when this is the case, right, because of how My is pulling down, if we were to sketch the deformation pattern, the deformation pattern will look like this due to Py. Okay, so for the deformation to look like this, we know that our moment about Z is in this direction. Okay, our moment about Z. And then if I call the top point alpha and the bottom point beta, right? So if I'm going to write out the stress now, right? So we know that once I draw the moment vector, we know that the tail end is in what? Tensile. The head end is in what? Compression. So from here, we can immediately write down that stress X at point alpha is equal to, now, Px over A, regardless of whether is it point A or point C, is always constant. Okay, so it's plus Px over A, right? Or whether is it at point A or point C, or alpha or beta, Px over A is always a constant. Okay. So now because our alpha is on top of the centroid, right? So it's in tensile, so it's equal to plus by mz over izz multiplied by y. And likewise, if you look at stress X at point beta, this is equal to plus Px over A. Now, because beta is below the what? Below the centroid. If you look at the green centroid, is below, and below your moment is in compression, or the stress in compression. So this is equal to minus mz over izz multiplied by y. So by visualizing, I hope by visualizing the moment vectors, things get less confusing for you or for me also. It really helped me a lot in visualization. Okay. Now, so now you know the difference between, right? Now you know visually the difference between what? Centric and eccentric. Next, I want to focus on what do we mean. Okay. I want to focus on the term. What do we mean by symmetrical and unsymmetrical? Okay, and I already gave you a hint down here where it's symmetrical, the moment is applied in one axis only, and unsymmetrical, the moment is applied in two axes. But it's more than that. Okay, it's more than that. We know if it's two moments, it's unsymmetrical. But I want you all to look at this situation where which I'm going to draw my my loading, which is different. Okay, so we have two different loading condition. Okay, so next we want to look at what is symmetrical and unsymmetrical. Okay, we want We want to look at this thermal wave. So we have, I'm going to draw two. Okay, we have loading condition number 1. So loading condition number 1, we have a beam simply supported again. Okay, simply supported. And we have okay, so this is point A, this is point B, and then we have a point C, and we have a certain point D. Okay, so A to C, we have a evenly distributed load. And at point D, we have a point load. Okay, and I'm going to draw our transformation. This is X, Y, and rotation about Z. And in loading condition number 1, our structure, the cross-sectional view look like this. Let me sketch with this. Then, so we have our cross-sectional view. Just look like this. Okay. So this is and now so if the cross-sectional view, if you ask me, Eugene, how does this transformation look like? So now this is Y, and then this is Z, and then we have our rotation about X. Okay, and then I'm going to call this point alpha. Over here is beta, and over here I call I, and over here I call J. Okay, and the geometric centroid, this is the geometric centroid. And then the next one, we have loading condition number 2. Now loading condition number 2, we are going to have a built-in. And then on this built-in, we have a what we call a gradient distributed load. Again, I will call this point A, and this is our point B. Okay, and then if we were to look at the cross-sectional view, the cross-sectional view looks like this. Okay, so this one have a cross-sectional view look like that. And then over here, this is our centroid. And again, this is my alpha, point beta, I, and J. Right, so we have two conditions now down here, right? So can anyone tell me, right, which one is symmetrical and which one is unsymmetrical? You can just type down, okay? Is it condition number 1, is it symmetrical? Or condition number 1 is unsymmetrical? Or is loading condition number 2 symmetrical or unsymmetrical? Just type in, just make a guess. So you write down condition 1 symmetrical, condition 2 unsymmetrical, or you can write condition 1 and 2 unsymmetrical. What is it? Come on. I hope someone is there, no? Anyone? I'm looking at the chat and no typing. Nothing. Anyone? Don't be shy, you know. If not, condition 1 symmetrical, condition 1 is unsymmetrical, condition 2 is symmetrical. Frank. Yep. Both are symmetrical. Yep. Anyone else? So I'm going to ask Bhagava. Oh no, we are getting merchant. You say both unsymmetrical. Okay, I'm going to ask Bhagava. Why do you say that why do you say that both are symmetrical? What condition do you say that? Can you speak or you can't speak? You are right. Okay, you're not wrong, but you're right.
Yeah,
Okay.
Professor, can you hear
Yeah.
me? Yeah.
Yeah.
I
Yeah.
think since like the loads are perpendicular to the centroid, so one of the faces will be in compression and the other one will be in tension. Is it because of that?
So you're partially right. Okay, not quite right yet, but partially right. So let me explain. Okay.
Yep.
Right. So whenever we look at a structure like this, right, we only calculate where failure will occur. Okay. So I'm just assuming a failure will occur at point F. Okay. Point F is where failure will occur, and down here we know that failure will occur here. Okay. So when we calculate the failure, what we get is we will get our moment about Z max. Over here, we will also, at our failure, we will have our moment about Z max. So when we apply the formula, right? So when we apply the formula, so down here, there's a certain distance we call y1. And over here, there's a certain distance we call y2. And then over here, we have a certain distance called y1. And over here, we have certain distance called y2, right? So when we apply the formula, right, and then we know, right, however things are bending because the depth of the deformation pattern, we know that this is our moment about Z. This is also our moment about Z vector. And also for this one, is different. This is our moment about Z. So we have a counter moment. Okay. Why that's the case? Because over here, the deformation will come down this way, whereas this one will come out in a smiling face. You can see why I draw the moment that direction. So if you look at the left-hand side or loading condition 1, stress X at point alpha is equal to minus mz over izz multiplied by y1. And also, if you look at stress X at point beta, the formula is also the same. When the formula is the same, the stress state is the same. So from here, we realize that stress X alpha is equal to stress X at point beta. This is the condition for symmetrical. Nothing to do with whether the structure is loaded symmetrically or there's or it's not a geometrical function. I mean, it's not physical geometry. Okay, it is based on stress. Okay, it's based on stress field. Okay, let me do again. So if you have stress X at point I, right? So this is equal, so we know that it's under tensile mz over izz